Okay, so we were saying from our trials that the internal rate of return was not encouraging. So to get a CER of 30%, we have to take a small discount rate, which sometimes is a limiting factor because, as we said, it depends on the owner of the project. So in general, A is around 10%. So 5% will be really a restricting value, and not any investor will go through it. Okay, that's why we need to reconsider the problem and try to come up with strategies to make the project more profitable. Okay, uh, one of the main, if you want, ideas will be to reduce the investment. And this is feasible. Why? Because, for example, let's say if you want to buy a car, you can buy it from Europe, you can buy it from China. It's true that European cars, let's say, or American cars have good reputation because they were on market from long time ago. But if you compare the performance of actual cars, you can see that even if a Chinese car are able to compete with these other cars as performance. So why not? So if I don't here, I have to reconsider my case. No need to why I should why I should put $12,000 if I can buy a turbine with same performance, let's say from China, with a budget that is much smaller. Okay, so this can be by reconsidering, if you want a compromise. So you will do a compromise between performance and cost. So you can say it's fine. Let me buy a turbine from China, not from USA. And I know that even if it's from USA, maybe it's manufactured in China. So why just to have the good reputation? I want to buy it. Let me reduce the cost and use good characteristics with a lower cost. So you can compromise uh, between characteristics and cost, and you can do a small research. If I can find a comparable turbine of good performance with a much lower price. Okay, so in this case I can do some research and decide on another turbine with same performance, and I need 3 kilowatt to cover my need, but I can let's say buy another from another source, even if it's not European or even if it's not from USA. It's fine because it's working well. And I can see that it's working well in several other countries. So why not? So this is one of the main strategies that I can use to reduce the investment. Sometimes we can see if it's possible to reduce maintenance, for example. But in general, if you reduce the maintenance cost, this might affect the lifetime, and it can affect the performance. Okay, that's why this is questionable. You are not sure that you can do it because you need to have a good effectiveness of your system. You need it to operate in a good way for the whole lifetime. So in general, this strategy is not widely used. Another possibility, okay, what can we do also, for example? So we talked about the investment, we talked about maintenance. In case here you have your, if you are working just to install a system for your home, you cannot play a lot with the selling price, okay? Because this is imposed from generators. So here you cannot play with it. But let's say you have another application. Let's say you are producing electricity from your turbine and you want to sell this electricity, then you can play with this. Okay, and in many countries, when we use renewable energy, the government will force people to buy it even at a larger price than generators. So whenever you have, if you want, the power of a government that can impose prices, that can impose to use this this renewable energy resource, you can impose selling prices. You can say, for example, let me impose, instead of a selling price of $0.1 per kilowatt hour, let me impose for the first year to sell it at $0.13 per kilowatt hour, then for the second year at 0.12, then for the third year at 0.11, etc. And this strategy was used a lot to motivate renewable energy projects in developed countries, because the government has the power to force people to buy electricity from renewable projects. And because they can impose on them taxes, they can impose on them if you want to buy a certain percentage of electricity from renewable energy. If not, they will cut electricity. They will not provide them with enough electricity, or they will make them pay taxes. So whenever you have regulations and in a country, and the government is powerful enough, you can impose larger prices, even if these prices are not competitive with the market. And this helped a lot renewable energy to be on the track, because as we discussed together in class, the main limitation of renewable energy at the first stage was the high cost. You have a high cost of implementation, and that's why to be able to pay back these systems, you need to come up with a certain strategy. You can enforce, for example, a larger price for the first years, and then it can be reduced with time. And this strategy was used in several countries. So from here, the selling price can play a good role in affecting the net present value. Another factor can be the number of operational hours. Okay, so we can discuss the possibility of increasing the number of operational hours. Of course, if we increase them a lot, then we have more maintenance. This will affect the lifetime. So we can, if you want, work in a acceptable range. So let's say I told you at the beginning the number of operational hours should be between 10 and 18. So you can go to extreme and say, let me operate 18 hours, even if this might lead to some fatigue of my turbine, but at least I can gain more and more money. Of course, you should study the effect on the lifetime, but if we consider that the lifetime will not be affected a lot, and we can consider that the maintenance also will not be increased a lot, we can go with this and find what will be the net present value if we operate up to 18 hours. So this can be several strategies that can help us to have a more encouraging project. Okay, and then also here we can ask ourselves questions in several ways. So let's say we want to study what is a good investment. What is an investment price that will be okay for us? So you can do it in the reversed way. Sometimes you might try, you say, if the investment is 10,000, let me do my calculations. But also you can do it in the reversed way. You can ask yourself, for example, if I want a high internal rate of return, let's say I want to impose an internal rate of return that is acceptable and that is very encouraging, for example, let's say 20%. If you say I want to have an internal rate of return that is 20%, what should be my investment? If I fix other parameters, what should be my investment? And based on this, you can see if you can find in the market a turbine with this price that will give you comparable performance. Okay, so now all you have to do is to go back to your equation and then do it now in the reversed way. You have the IRR and you want to calculate what should be the price in order to get this IRR. So all we have to do then is to say the net present value should be at year 20 should be 0. Okay, and here it's much easier to calculate it because you have a, so the equation will be much simpler, as we'll see together. So 0 equals minus I, which is to be calculated, okay, plus So 1533 minus 360 times the expansion of the series, okay? And now A is not unknown. We know the internal rate of return. We put it equal to the internal rate of return because we impose the net present value to be 0. So it's 1.2 to the power 20 minus 1 over, as we said, A times, so 0.2. Please, when you replace A, it's in the fraction. It's not the percentage, and you don't put 20 here. It's the fraction, 20%, 20 over 100, 0.2 times 1 plus A to the power 20. So times 1.2 to the power 20. I did something wrong in this equation. Who will tell me what is wrong here? What is wrong here in this equation? Plus the salvage, let's say 400 over. Who can tell me what is the error here? 360 represents what? This is the maintenance cost. And we said that the maintenance cost was based on the investment, okay? It's a 3% of I. So I cannot say anymore that it's equal to 360, okay? Because I should put here a 3% times I. So 0.03 times I, okay? So please pay attention. Any term that is related to I should be replaced by its corresponding value in the equation, okay? So now the only unknown in this equation is the investment. So it's much simpler than having A as unknown, because you can calculate the coefficient of I, you rearrange your terms, so you can find nearly what should be your investment, okay? And here we can get that the investment will be around $6,518. Okay, so you see, you should go down from 12,000 to dollars to $6,518 if you want an internal rate of return equals to 20%. Okay, which is a large difference, but you can find, as we discussed together, you can find this price with comparable performance. Okay, so let us say you did your research and you was able to select a turbine having this price. Now, next step, you can find, if you want your CER. So of course you will expect to get a high CER here, okay? Because already the IRR is really high, so 20%, okay? So for example, let's say if I ask you what is the discount rate for which the CER is equal as last question, 30%. So it's the exact same equation, but now I replace the investment by 6,518. So to get CER, minimum, equals to 30% of I use the previous equation, but just now I update I. So I put, instead of 12,000, the value that we got, $6,518. Okay. And now we can expect that A will be much larger than 5%. Okay. So we were able to increase the IRR from 7.5% to 20%. So if we use our equation, which is 0.3 times the investment, which is $6,518, equals to minus the investment, which is minus 6,518, plus the gains, so plus 1,533, minus 0.03, so minus 3% of the investment, okay, times 1 plus a to the power 20 minus 1 over a times 1 plus a to the power 20 and plus the salvage value. هلا here, look, هلا here we can consider, of course, the salvage value will vary. Okay, so here to be more accurate, I can update the salvage value for you. Okay, so I can tell you, because this turbine is of lower cost, the salvage value will be lower. So I can tell you, for example, update the salvage value now to have a more accurate representation to 200. Okay, so now the salvage value is, let's say, 200 over 1 plus a to the power 20. Okay. So now, if you use iterative method, or if you use your calculator, you get a equal to 14.8%, which is very acceptable. So because we said in general, an acceptable rate is 10%. So if you use 10% as a discount rate, you will get, of course, a CER that is larger than 30%. Okay, so you are on the safe side. For any value of A below 14.8%, you will gain more than 30% of your investment. So you were able to make your project much more profitable by just considering a smaller investment. Okay. Now, as I told you also, if you consider another type of projects, so in case you want to sell electricity, you can play with the price, and playing with the price can affect also your gains. Okay, so in case, as we said, the government is responsible of the project, this will give much more, if you want, flexibility in the selling price, because you can impose on people to buy electricity from renewable energy projects, and therefore you can increase your gains. Okay, so just to consider how we can see the effect of a varying selling price on the analysis. Just this make a little bit the equation more complex, but as we'll discuss now. So just we need to write our terms, and we decompose our terms in a certain way, as we'll see together, to still have a geometric series. So for example, if I tell you that the selling price is, for example, 0.1 dollar per kilowatt hour for the first year. Okay, so here, for example, because we reduced a lot the investment rate, then we can say we start with a price of $0.1, but we can reduce it after, because our project is promising. So we have the flexibility to offer good prices, because this will be also more attractive for people. So in this way, even if you don't force people, they will buy electricity from this resource. So always the strategy in renewable energy was first to impose regulations, if you want to put it in the track. But once you put it in the track, you can, from technological advancement, from, if you want, reduction of prices, you can be more competitive in the market, which will make people select this choice without any enforcement. And this is what we need to do at the end, because in general, whenever you impose something, if you don't always put taxes, okay, or you put some penalties, no one will use such system. But to make it competitive, you need to at the end to sell at lower price. So when you enhance the state of your project, you can go to lower and lower prices, and you can say I will start with a selling price of 0.1, and because I am getting good gains, I have the option, I have the flexibility to reduce. So I can say, for example, for the first year, I can start with this selling price. So this is for year one. Then for the second year, let's say I can reduce by 10% the selling price. I can have it equal, let's say, to 0.09 dollars per kilowatt hour. For year two. And then let's say for the remaining years, okay, so for remaining years from 3 to 20, let me say I will sell it at $0.08 per kilowatt hour. Okay, and then I will say for a discount, I can now impose the actual discount rate. Okay, so now let's say for the investor, the corresponding discount rate is 10%. Okay, and I want to calculate, let's say, my gains at the end of lifetime. So all I have to do is to say net present value of this project after 20 years for a discount rate of 10%. So for A equal to 0.1, okay, is equal to. So first, I will use the updated price because I was able to put this strategy of low selling prices because I have a good investment. So I will use the updated turbine price minus 6,518. Then I will say plus, as we said, we should pay attention here that the selling price is not constant. So whenever you have a varying selling price, you should divide your net gain with years. So for year one, okay, for year one, you need to determine what is your net gain. So for year one, it will be identical to previous years, to previous analysis, because as we said, the price was 0.1. Okay, so what you will have to do is to say for year one, okay, the gain will be. So as we mentioned, we have to consider the number of operational hours. So let's say it's 14 hours. Okay, so 14 hours times the power of the turbine times 3. This will give you the number of kilowatt hour per day. You multiply by 365 to get per year, and finally you multiply by the selling price to get the net to get the gain for this year. Okay, so for example, this is already calculated. This will give us 1533. Okay, but now, of course, because the selling price here was reduced by 10%, so also the net gain, the gain per year will be reduced by 10%. Okay, but to get the net gain, you should subtract the maintenance. So now we can say that for the second year, it will be equal to 90% times $1,533. Okay, so here it will be equal to $1,379. And for remaining years, it's this amount multiplied by 80%. So we'll get 1,226 Okay. And now, then we should divide our summation. Okay. We cannot now take the whole summation as previously, because we need to consider for year one, we'll do the net gain. So for year one, it's 1533 minus the maintenance cost. Okay, so let us put here the maintenance cost to not write it each time. So the maintenance cost is 3%, so 0.03 times the investment, which is 6,518. Okay, so minus the maintenance cost. Because it's the first year, I divide by 1 plus a, so 1.1 to the power I, which is 1, because it's year 1. Okay, now plus for the second year, I have instead of 1533, my gain will be reduced. It's 1,379 minus the maintenance cost. And now, because it's for year 2, I divide by 1 plus 1.1 square. And now, for the remaining years, I can apply the summation. Okay, so for the remaining years, I can apply plus summation from year 1 from year 3, sorry, to year 20 of 1226 minus the maintenance cost. Here, of course, we are considering constant maintenance cost. But if the maintenance cost is varying, then for each year you put the corresponding cost. Okay, and when you have stability, so the maintenance cost is not changing anymore, and the selling price is not changing anymore, you can apply the summation. So over 1.1 to the power I. Okay, and then here in this case, also your calculation is simple because you don't have any unknown. So you can just get this summation from the calculator, okay? And you can find what will be your net present value for this discount rate. Okay, so no iterative procedure is needed here because there is no unknown except the NPV at year 20. So you just replace your maintenance cost. You can use your calculator to calculate this summation from 3 to 20, and then you can get what is the NPV. And of course, then based on this, you say the capital enrichment rate is this value over the investment. And you can expect, of course, a relatively large value because you worked on a discount rate much smaller than 14 point, the value that you got to get 30%. So you got that the discount rate should be 14.8% in order to have 30% gains. But here you reduce to 10%. It's true also that you reduce the selling price. So this might affect a little bit the value. So to be able to judge exactly what is the final CER, you do your calculation. But because the discount rate was significantly reduced, you can expect to get an acceptable result above 30% for your CER. Okay. So in overall, this was a little review on how we can use the main concepts, the main factors to judge if a project is profitable or not. Of course, there is salvage value, Elio. Yes, I'm sorry we forgot to add it. Of course, because we are considering the end of lifetime. So it's year 20. So just we have to add plus 200 over 1.1 to the power 20. Thank you, Elio. Yes, it's right. Okay. And now we can assess exactly what is the percentage of gain corresponding to this case. Now, they can also ask you here, what is the payback period? Okay, so you can find then if they tell you what is the discounted payback period, okay? So here, if they tell you calculate the discounted payback period, not the non-discounted one, so you should take into effect the discount rate and the value of money with time. So calculate now the discounted payback period. Okay. Now to calculate the discounted payback period, here we don't include Elio's salvage value because we expect, of course, to have the discounted payback period before the end of lifetime. Since we are getting positive NPV values at end of lifetime, this means that NPV was 0 before the end of lifetime. And therefore, to calculate the discounted payback period, we don't include the salvage value because we didn't reach yet the end of lifetime. So we write, what is the condition to have the discounted payback period? It is the value of the number of years for which the net present value now at year n, okay? So we need to determine what is the number of years for which the NPV for a discount rate of 10% is equal to 0. So we want to search for n. What is the value of the number of years for which we get a net present value equal to 0? So now all we have to do is to write, if you want, the previous equation, but now not to year 20, to year n. And of course, we exclude the salvage value because we didn't reach the end of lifetime. So we say 0 is equal to minus 6,518 plus, so as we said, you can directly deduce this equation from the previous one. You put that for the first year, it was 1533 minus the maintenance cost over 1.1. So this term is still the same. Also, the second term will be the same. Okay, so plus the second value, which is 1. So it was 13. I think, let me 1 second. Yes, 1379. So 1379 minus maintenance cost over 1.1 square. And so until now, no difference. Now we'll start to have the difference because now the summation will not be to year 20. Okay, the summation will be from year 3 to year n. So we want to search for the value of n, okay, for which the NPV at year n will be 0. And we said that for the third year, the value of the gain is 1226. So 1226 minus the maintenance cost over 1.1 to the power I. Okay, so now from year 3 to n. Okay, now in this equation, the only unknown is n. Okay, as we said before, you can use your calculator to solve for n. You can also convert this term to geometrical series, and in this, but please pay attention. If you want to use geometrical series expansion, you have a condition. The condition is that the summation should be starting from 1, okay? And one strategy to have the summation starting from 1 is to just play with numbers a little bit. So you divide your summation in this way. You say, let me put it, this summation, I can decompose it as a summation from 1 to n, okay, of this term, but I should subtract the first 2 terms. And the first term of this summation is 1226 minus maintenance cost over 1.1. And the second term is minus 1226 minus maintenance cost over 1.1 square over 1.1 square. Okay, why we did this? Because in this way you can replace this summation by the geometrical expansion, okay, which is the constant, which is 1226 times 1.1 to the power n. N is your unknown, the number of years, okay, minus 1 over 0.1 times 1.1 to the power n, okay? And in this way, your only unknown in this equation will be n. So you can solve it without, if you want, without the shift solve option of the calculator. You can find then what is the value of n. So you have a lot of methods, of mathematical methods to get n, or by trial and error, or by using the calculator, or by replacing the geometrical series by this expression, and then the only unknown will be n. So you can get the value of n. And of course, you expect a good payback period here, discounted payback period, because you got a very high internal rate of return. Yani your calculation was based on an internal rate of return equal to 20%. And since A is 10%, which is much smaller than this rate of return, then you expect to have a relatively short payback period, discounted payback period. Okay? Yes, of course, minus Cm. 1226 here, minus Cm. It is the constant that we got outside of the summation, of course. So it is the same constant that we used here in the first term and in the second term. But in this way, by just playing with these numbers, by subtracting the first two terms, we transform the summation from 3 to n to a summation from 1 to n. Okay, and then we multiply the same constant by the geometric expansion. Any other question on this? And there is no salvage value here. Why? Because as we mentioned, no salvage value because we didn't reach the end of lifetime. We reached year n, which is much smaller than 20. So you only account for salvage value in calculating the net present value at the end of lifetime. If you want to search for the payback, for the discounted payback period, you don't, or for the non-discounted payback period. In both cases, you don't include the salvage value because the salvage value will only you will only take it at the end of lifetime. You will not sell your system before the end of lifetime. That's why for payback periods, we never include the salvage value. Okay? Other question on this? Okay, so this example was a revision of the main concepts. Next time, we'll start with the new material. Thank you.